Okay, this is a conceptually quite challenging question and also algebraically quite challenging question. So I definitely put this in the challenging mechanics question category. However, it does follow the standard rules of solving force-based and moments-based mechanics problems. So make sure that you've read the text carefully. And let's start trying to draw a force diagram, which should be the first thing we try to do with any force-based problem. And once we've got a force diagram, we're then going to draw a resolved force diagram, which we can then actually use to set up equations. That's again the standard procedure for solving mechanics force-based problems. So, reading the text, the first thing I really spot, apart from the fact that, okay, the rod is length 3A, but that's already on the diagram. The end A is in contact with a smooth vertical wall, and for that reason we can draw a reaction force from that point A sticking directly, perpendicularly out from the wall. There is no vertical component of the reaction at A because it's smooth. Okay, next, reading on, we have this load of weight W at the end D. Great, stick that on the diagram. Gravity pull downwards, so the weight acts downwards. Okay, reading on further, we have these smooth pegs that are fixed at B and C, and specifically B is above the rod and C is below the rod. Now, hopefully you can sort of think about, you can sort of picture this rod. But if you can't, it doesn't matter. Just respond to the text and you can still do this problem even if you can't imagine this physical situation. Since they're smooth pegs, B must be pushing straight into the rod and therefore there's a B force that way, and C must be pushing straight into the rod, again sort of perpendicularly to the rod, and that must be pointing the other way. So one way of thinking about this is to imagine now pulling down really hard on D. Let's pull down here. What's going to happen? Well, the rod is going to press hard against C, and therefore peg C is going to push back hard against the rod. But similarly, if you're pulling down on D, the bottom of the rod's going to want to move up, isn't it? It's going to want, the whole rod's going to want to pivot around C. So the rod's going to push up on peg B, and therefore peg B is going to push back on the rod like this. So those blue forces that we've drawn are not just forces per se, they are forces acting on the rod by the weight or the pegs or the wall. It's all forces on the rod we're interested in. Great, that is a complete force diagram. The rod, we don't need to worry about the mass of the rod because it says it's a thin and light rod. Thin and just allows us to place it in this nice gap between B and C without worrying about bending or anything. Light means it's got basically no or negligible mass, so we don't need an extra centre of massy sort of thing going on for the rod. That's really important here, otherwise if you include that you just won't be able to do this question. Right, next step, resolved force diagram. So draw it again. B and C are already perpendicular to the rod. R and W are not. So we're going to split up R and W into their components. Now to do that, let's first look at W. Now look up here. Where's the angle? The angle theta is defined here. Where's the angle theta here? Well, it can't be this angle, can it? Because that's too big. And also, if you complete the triangle round there, using the rod as the hypotenuse, and down here, you'd have a 90-degree angle here, and this angle up here would be 90 minus theta. So if that angle there is 90 minus theta, then there must be a little one just in here. You can see I've just drawn that there, where theta must be. That rest of it must be theta. So once we've got theta there, we know that this one must be W cos theta because this component here is touching the angle, so it must be cos. And the other one that's not touching the angle must be sine. So okay, we've done W. R is a bit easier because we've already got theta there already. So the component of R that's touching the angle, again this time this is the one on the rod, parallel to the rod, that's going to be the cos one. and the other one's our sine theta. Okay, now we have a resolved force diagram. We're doing really well. Right, start writing down some equations. Don't worry about what you're aiming for yet. Show that the normal contact force at C, show that C equals this expression here. You're not going to be able to go anywhere near figuring that out for 5 marks unless you set up all the equations associated with this force diagram. So set them up. First one, let's look at forces parallel to the rod. Well, there's only two. There's r cos theta pushing into the rod here, and there's w sine theta pushing into the rod the other way at the other end. So those two forces must be equal. Perpendicular to the rod, there are 4 forces, but C is kind of pulling that way, and the other 3 forces are all pulling in the opposite direction. So I'm going to write that C is equal to the sum of those 3 other forces. And finally, moments gives us a third equation. Sometimes there's a fourth equation, which is to do with using F max equals mu r if something's in limiting equilibrium. But that doesn't apply here. Everything's smooth. There's no friction here. So the only other one we can do is moments. I'm going to take moments around A, and since the rod is in equilibrium, it's not rotating, there should be 0 total moment about A. Now there are going to be 3 forces. If we don't have to go back to this. We can still use our resolved force diagram. If we're taking moments about this point here, A, then we can ignore forces whose lines of action pass through A, because their distance is 0. So I can ignore r cos theta and r sine theta. It's just the other, the other 4 forces. I'm also going to be able to ignore w sine theta, because again, its line of action passes through point A. So I'm going to start off by writing BA, because from here we've got force B, which is perpendicular, and it's A away. Remember that distance is A. I just haven't put it on my resolved force diagram. So B times its distance A. Subtract, because it's going the other way, C times 2A. And then plus W cos theta times 3A. And that must all equal 0, total moment 0. Now, before we go any further, I'm going to simplify that equation. I'll spot that there's an A in every term, so I can cancel those and write that as B minus 2C plus 3W cos theta equals 0. So we now have 3 equations. We are asked to show that C is equal to this expression here. So since I've already got C equals here, I'm going to use this as my kind of base equation and substitute stuff into it from the other 2 equations. So let's highlight that and start with that. C equals. Right, what's in our target equation? There's a W and a theta and nothing else. So anything here that's something other than W or theta has got to go. Right, starting with this term, we have an R. The R's got to go. How can we make it go? Let's use this equation here. If we rearrange this, we'll have R equals W sine theta over cos theta. So if I substitute that in for the first term, we're going to get W sine theta over cos theta, which is our R, times sine theta. So we're actually going to get W sine squared theta over cos theta. Okay, the next term is a B. I want to get rid of that as well. Easiest way to do that is from here. I can rearrange this equation here to make B the subject, which makes B equal to 2C take away 3W cos theta. So there's our plus B. I've dealt with this B now using the bottom equation, and then finally plus W cos theta. I'm allowed to use both of those, and that's that. Brilliant. We've collapsed this whole equation now to have just C, W and theta in, which is what we want. We just need to simplify it. So hopefully what we've got there simplifies to this. I'm going to take away 2C from both sides. And I'm also going to spot that we've got we've got take away 3W cos theta plus 1W cos theta there. So that's altogether take away 2W cos theta. Next, see what I've done there? I wanted a common denominator, so I've just times top and bottom of this fraction by cos theta. And that allows me now to combine it into a single fraction. So minus c is equal to, I'm going to factor the w out as well. And if you combine that into a single fraction, you get that. Now, just to save a bit of space here, I don't really want minus c equal to this. I want plus c equal to this. So I'm just going to use a little trick. I'm going to make that plus c. I'm going to swap over these terms on the numerator, which multiplies both sides of the equation by minus 1. So I'm just going to erase that and rewrite it. Great, now I've got c equal to that. Now again, just compare it to what we're trying to work towards. This has got no sines in it, has it? It's just got coses, but we've got a sine. So let's get rid of our sine squared, using the fact that sine squared theta is equal to 1 minus cos squared theta. That's there. And then that rearranges to the required expression. And we're done. 5 marks. Okay, so far I've spent 11 minutes on this question. But look, how many minutes have we got altogether? We've got 5, 6, 7, 8, plus 6 is 14 minutes. I've got 3 more minutes. I'm going to take a little bit longer than that, just to explain things. But this is a hard question. You can expect to spend, it'll be near the end of the paper, so you can expect to spend 15, maybe even longer minutes on this. Right, clear some space. We now, in this bit, we need to find, just says find b. Do the same thing, but find b this time. Well, we've got the b is equal to 2c take away 3w cos theta, so I've written that here. We know c because we've just found it here, we've shown that, so we can substitute that in there, in here, and just simplify. So substitute, and we need to simplify that. Again, well, I can spot that we can factor a w out again, there's w in both terms. I also want a common denominator, so I'm going to use that trick from before. Here, you can hopefully spot what I've done there. I've just multiplied through the 2 I've just times by the numerator here. And now I'm going to, and the w I've factored out. I'm just going to use that times top and bottom by cos theta trick again to get a common denominator. And then when you do that, you get this very elegant result, I think. Just the fact that it compares so similarly to the result for C. The only difference is this minus 2 instead of minus 1. It's quite a nice result. It gives you confidence, I think, that you're going in the right direction with this problem. Okay, so I'm just going to write that there, and then I'm going to erase my working at the bottom of the screen again. Part 2, hence show that the value of theta is at most 35.3 degrees. Right, hard. To do questions like this, you need to think about what's limiting this system. What's the furthest something can go? Well, let's think about this a moment. If I were to, let's look up here at the diagram. If I put a hugely heavy weight on here, what's that going to do? Well, it's just going to increase C. It's also going to increase B. And, I don't know, it's probably going to increase R as well. It doesn't look like that's going to limit things. If we've got a rigid rod that's not going to bend, I don't think there's any limit to W. Well, what else is limiting here? What if we make W really, really small? Well, it's hard to sort of imagine what will happen then. But is it possible that B could disappear altogether? There's our limit, right? Our limit is that B could simply just vanish and there's no contact force at B. There's going to have to be a contact force at C because it's holding the rod up in the air. And there's going to have to also be something at R, because if C has got a component in the left direction, which you can see it has a bit, then R must be non-zero as well. It all just comes back down to B. It's possible that B could be 0. And that is what we need to work with. So remember that question to ask yourself, what is the system limited by? And then the answer in this case is that B has to be non-negative. It can only go down to 0. I realise actually now making this video I should have greater than or equal to there, but you can still do this problem, it's still fine. So if B has to be positive, and we've got an expression for B that we just worked out in the last problem, and notice it did say hence, so there's a bit of a clue there that you need something you've just worked out. So I've just set that up. B greater than 0. Solve. I'm going to divide both sides of the inequality by W. I'm also going to times both sides of the inequality by cos theta. Still get 0 on the other side. And that means 3 cos squared theta minus 2 must be positive. The whole thing simplifies to that, which we can square root to get that. Note that technically I need plus and minus here, but we're only dealing with small, theta is clearly somewhere between 0 and 90 degrees, and therefore cos theta is going to be positive. So I don't need to worry about a negative value there. And that gives us theta has to be at least 35.3 degrees, as required. And finally, last part of this question. We have to show that it's not possible for the magnitude of the reaction at A to equal the magnitude of the reaction at C. In other words, show that R cannot equal C. So a good way to do that is to proof by contradiction. That's exactly what we're doing here. Show if we assume that R equals C, see what happens. Hopefully we'll find that something breaks somewhere along the lines. So why am I able to write R equals W tan theta? Well, that just comes from this equation here. Notice I've left all these here to use later. So I've divided again, like I did before, I've divided both sides of this equation by cos theta, but this time I've written it as tan, because why not? I could have written it as sine over cos, it doesn't make any difference. So we have R equals this, and we have that C equals this. So I'm going to set W tan theta equal to that expression for C. Great, this looks easy to solve, or to simplify. We can cancel the W's. And I'm also going to times both sides of the equation by cos theta to give that expression, that equation there. Tan times cos is sine, so we have sine theta equals 3 cos squared theta minus 1. To try and solve that equation, I'm going to have to get everything in sine or cos, and it makes sense to try and get everything in terms of sine, because we can change the cos squared to 1 minus sine squared. Expand. Simplify, bring everything to one side to make it a disguised quadratic, factorise it, set each bracket equal to 0, and we get those two things there. Sine theta equals 2/3, which is perfectly plausible, and sine theta equals minus 1, well, that's irrelevant and nonsense, because that would require theta to be 270 degrees or minus 90 degrees, which is just not going to work. So we can just say no, disregard. The other one gives us theta equals 41.8 degrees. What's wrong with that? We're expecting a contradiction, remember? Do we have one? Yes, we do, because in part 2 we showed that theta was at most 35.3 degrees. And we've shown that for R to equal C, theta has to be 41.8, which is impossible. So we have ourselves a merry little contradiction, and therefore R cannot equal C.